After knowing the stresses acting on your material and the shear stresses acting on your sandwich material, alright, then we can talk about what is the maximum deflections of the material, so that you know that whether it is safe or not. Alright, what is the deflection? And therefore, to get a deflection, this is the term delta. Your delta is your maximum central deflection. Okay, and the equations may seem a bit tedious, but it's quite straightforward. Your W is your weight or your forces, alright, which is what we have keep on saying. Alright, your W. Alright, this is the force. Or if you think about it, force is in Newton. Your weight is also in Newton, because weight is kg times your meter per second square. Alright, you'll get Newton. Alright, just the same thing lah. Okay, I'm not going into details, but I just need to know that this is the weight. Alright, so the force or weight is just the same thing. Alright, it's always given, or otherwise you can calculate yourself. And then is the weight applied onto your sandwich? Like, okay, I repeat again, in case you use the weight of the sandwich panel. So the weight is the applied force. It's not the weight of the core, or the weight of your face, or your weight of your sandwich panel. Alright, be careful of that. And the length, I think, is straightforward. Alright, is this particular length. Okay, it's pretty straightforward. While the D, alright, is the one that we have keep on saying. The D is the standard, your flexural rigidity. You're gonna calculate this also. So I'll show you how to calculate this in a certain extent, that by using this cross-sectional diagram. The HCB, everything is all given to you. So it's quite straightforward already. Alright, while the area over this A over here is your AG is your shear stiffness. Okay, this whole thing is your shear stiffness. So your A is your BD square over C. So your B, your D square over C is all given already. No need to do anything. Alright, while the shear modulus of a core, you're gonna calculate yourself. Or it may be given, or nonetheless you may calculate. And the thing is the same as this one. This one is, if you remember from the previous lesson 6, or this lecture part 2, page 50. Alright, your shear modulus is for over here is for your laminate. Alright, where you're talking about the axial stiffness, if you remember. Alright, so this is for your laminate, but in our case, I think you can also use that. Alright, if you have only one laminate, because if you have only one laminate, alright, it's just one layer of core, then you can also still calculate yourself, and eventually you'll get this G thing. Alright, so if summation Q bar ij is actually your transform stiffness matrix. So if you only have one layer, then it's just simply the Qij bar of your this piece of core. Alright, and then after that you can multiply with h divided by n. Your h is your total thickness of your core. In case instead of laminate you use as core, then divided by the number of plies, which is only one ply. So it's the height is the total thickness of your core times your Qij. You'll get your Aij. So once you get this thing, so now what I'm calculating is actually for the core. I may be wrong over here, but this is what I assume. So once you get these, or your Aij have A11, A12, A13, etc. Alright, so A21, A22 all the way to this 3x3 matrix. So this A22, you'll use it for, sorry, it should be A33. So there will be A33 over here lah, okay? So A33 divided by your thickness, you'll get your shear modulus. Okay? So this is how you rearrange your stuff. Instead of a laminate, you can change it as a core material, and you can calculate for your own shear modulus for your core. I may be wrong over here, but this is how we will see things. I have a little time, let's make a sense out of this equation. Maybe we can know better. So the D itself, if you remember, is your flexural rigidity, where it is a measure of how well you can withstand bending. Alright, so D is how well you can withstand bending. Shear stiffness is how well you can withstand shearing. Alright, so the higher you are, as you can see, the lower your deflection. Right, so the higher of these values, the higher the denominator, the lower your deflection. This is what it means. So it's like a ratio between your weight your forces apply against its certain length. So it's like a moment because it's force times perpendicular distance. Alright, so your length is actually the perpendicular distance. So it's a moment against the stiffness of the thing. So if the moment is larger, you'll need a larger stiffness to keep the deflection low. So if your moment is low, then I think you get what I mean lah. So this part over here should be most likely the moment. Alright, so if the moment is high, you will want your stiffness to be high. So your stiffness to be high in order to keep your your overall deflection to be low. Alright, so the moment divided by the stiffness gives you the deflection. Okay, in case you don't know what the hell is deflection, then deflection is this thing. Alright, so you deflect a certain distance, alright, from the original system. So maybe this is your sandwich panel, okay, and this is the neutral axis or the middle part. And if I were to bend it, okay, if I were to bend this thing over here, as you can see, this neutral point to this neutral point, this distance I believe is the deflection. Okay, hopefully this is pretty clear. Alright, so the deflection is over here, this neutral axis against this thing, alright, at the middle point. So this is the central deflection, where it is also the highest deflection of your beam. Okay, because you are actually applying the force at the middle part. So at the middle part, it is actually the highest deflection. Okay, and another thing is the understanding of this small capital D. Alright, this small capital D, if you take a look, is actually the middle part of your so-called face. Alright, so this part over here is the middle of your face. Okay, and this is just the meaning of that. Just for you to take note of. Then because why is it middle? If you think about it, it's also relating back to your A times your C. Alright, if you remember in the video on bending stresses, is it? They're actually talking about the bending of your beam or solid beam. Let's go back to the solid beam. So don't mix it with our sandwich panel now. Alright, so sandwich panel, leave it there first. Alright, let's jump into the solid beam. If you remember the solid beam, we talk about the S as equals to A times C. Alright, so where the C is the distance from the center of the shaded region. Alright, so the shaded region is this one, for example. The center is actually this one, alright, which is called the C bar. Or otherwise, over here, this is the area. The middle is actually the C. Okay, so I will believe this concept is also being brought into now our sandwich panel. Alright, which is this one. Alright, if I were to show you it's the middle part also, but it's spanning across. So this distance, alright, the shaded region, alright, the middle part of the shaded region, which we previously called it C in the solid beam, now is D. Alright, from the neutral axis is D over 2, because this whole thing is D ma. Alright, so D over 2 is actually this one. So for you to just go around and check it out, the equations, and see the relationship between them, so that when revising is pretty much easier for you to understand, I believe. So I think this is it for the sandwich panel part. Alright, and I haven't derived the equations, but it's more on the applications and doing things blindly. So if I have time, then I'll just do up the derivation parts. But we have somewhat finished the sandwich panel, be it the construction or the equations, we have somewhat understood. And therefore we'll go on to the tutorial and see how we can so-called apply them. See you there.